Good morning, guys. So today we're going to be going over lesson 5.6, the properties of linear functions. And a lot of today's lesson will be a review of stuff that we did in grade 9. Tomorrow's lesson and the first few lessons of chapter 6 are also a lot of review of stuff that we did in grade 9. But this stuff is really important, and we'll be continuing on with this stuff into chapter 7 as well. So if you have any questions about it, please let me know. Okay, so the first thing that we're going to be reviewing in today's lesson is what rate of change means. So rate of change is also sometimes referred to as slope, which is represented by the letter M anytime we're writing equations or doing calculations. In a linear relation, the rate of change must be constant, and we calculate the rate of change by dividing the change in the dependent variable by the change in the independent variable. So just a reminder, the dependent variable is your y value, the independent variable is your x value. So these are the two equations that we use to calculate rate of change, and we'll do some examples with these later. So m is the rate of change, and then this little triangle here is a delta symbol, and what that little triangle means is a change in. So anytime you see that little triangle, it means a change in something. We also used that symbol in the physics unit of Science 10, if you remember it from there. So what this equation means is that the slope, or the rate of change, is equal to the change in y divided by the change in x. Another way of representing that is that our slope, or our rate of change, is equal to y2 minus y1 over x2 minus x1, where x1, y1 is a coordinate and x2, y2 is a second coordinate. So one of the things we're going to be doing today is identifying whether or not something is a linear relation. And you'll have to be able to do this in a bunch of different forms. So the first form is a graph. And anytime we're looking to see if something is a linear relation or not, what we're really checking to see is, does it have a constant rate of change? So in a graph, that just means that your line will be a straight line. It could be a straight line going across, or a straight line going up, or a straight line going down, or even a completely vertical line. All of those would be linear relations as long as the line is straight. If it is in an equation, you can always find the rate of change right in front of the independent variable, which is your x. So if we write this out in the form y equals mx plus b, which is the general form of a line, the slope is right in front of your x value. So in this example here, our rate of change would be 3. In order for this to be a linear equation, though, the x value, or the independent variable, must have an order of 1. So if we look at this example down here, y equals a half x plus b, as long as our x is just an x, it's linear. However, as soon as I have like an x squared or an x cubed or something like that, this is no longer a linear equation. Okay, so that's what it means by the x has to have an order of 1. As soon as the x is to the power of something other than an imaginary 1, it is no longer linear. And then you're also going to have to be able to identify whether or not you have a linear relation when given a table. So what we're going to do in that case is we are going to check the rate of change of each side of the table individually. As long as both sides are changing by a constant rate, then it will be linear. And you can check that by dividing pairs of rates. If all the quotients are the same, it is linear. So I'll show you an example of what that actually means. Okay, so in this example here, I have my table. My two variables are time and cost. First thing you want to do is figure out which one of those is your X and which one is your Y. Because time is always independent, that's going to be our X. And because the cost of something will depend on the time, that'll be our Y. And so then when it says to check the rates of change on both sides individually, what that means is over here, we're going to look for our change in X, which is just how much these X values are changing by. So to go from 1 to 2, that is a change of 1. From 2 to 3 is a change of 1. From 3 to 5 is a change of 2, because it's going up by 2. On the other side, from 75 to 125, that is an increase of 50. 125 to 175 is an increase of 50. And 175 to 275 is an increase of 100. So these are our delta Y values. Okay, so it's our change in our Ys. Now, if this graph or this table only included the first two columns, we would just see that the rate of change is constant for the X's and it's constant for the Y's. It's the same for all the X's and it's the same for all the Y's. So right away we would be able to tell that this is a linear relation. Because I have a different rate of change on the bottom, now I want to check it. And so we do that by saying, okay, I'm going to take the first two rates of change and I'm going to divide them because our rate of change is delta Y over delta X. So if I take those first two numbers, my delta Y is 50, my delta X is 1, so that would be 50 over 1, which is 50. That's my rate of change for the first pair. The second pair are the same, so that would be my rate of change for them as well. Let's try the third pair. This time, it's going to be 100 over 2. My delta Y divided by my delta X, and it's still 50. So because these are the same, my rates of change are the same no matter which pair of delta Y and delta X I use. They're the same, therefore this is linear. Okay, I can also kind of tell that without actually doing the calculation, because to go from 1 to 2, I'm doubling my rate of change, and to go from 50 to 100, I'm doubling my rate of change. So both of these rates of change is doubled at the same time, which means that it's linear. If this side, our X side, had done 1, 2, 3, 4, and had just maintained a rate of change of 1 the entire time, and our Y's still looked like this, then when I divided 100 by 1, I would have a different rate of change, and that would mean this is not linear. Okay. The last thing that we're going to be looking at as far as identifying if something is linear or not is ordered pairs. And if you do have ordered pairs and you're trying to figure out if they're linear or not, you just plug them into a table like this. So if I had a set of ordered pairs like this, I would just put them into an XY table. Again, ordered pairs are always in the order of X and Y, so I would write it as 1 and 5, 2 and 10, 3 and 20, and 4 and 25. Then I would check my rates of change. So this is going up by 1, and by 1. On the other side, it's going up by 5, and then 10, and then 5. Because my x's are staying constant the whole way through, and yet my y's are not, I know that this is not linear. You could also check by dividing your pairs again. So I could do 5 over 1 is 5, 10 over 1 is 10, and because these are different, therefore it is not linear. So I just did this 5, my delta y divided by the delta x, and got 5, did this delta y divided by its delta x, and got 10. So when they're not the same, it is not linear. Okay, and then the final part of today's lesson is to actually calculate rate of change on a graph, which again is something that we did in grade 9, but we will review the two different methods quickly today. So the first method that we're going to look at to find the rate of change of a graph is to use the rise over run formula. This works well as long as both scales are the same. That's when it's the easiest. So here, my scales are all going up by 1, both on the x and y axis. So it makes it really easy to do rise over run. When you do rise over run, you always want to read the line from left to right, the same way that you read a sentence. So read line from left to right. So I'm going to start on the left and move towards the right. And then as I do that, I'm just going to pick any 2 points along the line. So I can pick this is number 1 and this is number 2, or this is number 1 and this is number 2. I want to pick any 2 points that are beside each other and are actually like on the grid somewhere, not just like in the middle of 2 points. Okay. Then I'm just going to say for my rise, that's how far up and down do I have to go to get between the 2 points. So in this case, to get from this, I'm going to call this my first point and this my second point. To get from the first point to the second point, I am going to have to go down 1. Down 1. And the way we represent down 1 is with a -1. Anytime you go up, it would be positive. Going down would be negative. And then my run is just going to be from the left to the right. How many spaces over do I have to go to get from my first point to my second point? And the answer is 1, 2 spaces. So my run is 2. If you do it like this, if you always read the line from left to right, your run should always be positive. Okay, always positive. And then your rise, again, will be negative if you're going down, positive if you're going up. And then our final answer here for our slope is just the rise divided by the run. So -1 over 2, our slope is -0.5. Okay. You would always put this in lowest terms if possible, but that is already in lowest terms, so that's our answer. Okay, method 2 involves using either our either one of our 2 formulas. So either slope is a change in y over a change in x, or slope is y2 minus y1 over x2 minus x1. Again, both of those formulas mean the exact same thing. The first version is just kind of a shorter way of writing it, but it still means the same as the second formula here. So this time we're going to start by picking any 2 coordinates. Pick 2 coordinates. Okay, that should be your first step. So I'm going to pick this coordinate and this coordinate. It doesn't have to be a coordinate that's on the axis. Any coordinate that is easy to read accurately, you could pick. So I could pick this one as well. I could pick like this one, if that's right on the line. Okay, any two coordinates would work. So I'm going to pick this one here, which is 0, 2. And then let me actually change it up to one that's not right on the axis. Let's do this one, 3, -1. Okay, doesn't matter which two coordinates you pick. I'm then going to call one of the coordinates coordinate number 1 and the other one coordinate number 2. Again, doesn't matter which one is number 1 and which one is number 2. And then don't forget, every coordinate is in the order x, y. So when I plug this into my formula, and again, it doesn't matter which of those formulas you use, our y coordinates are on the top and our x coordinates are on the bottom. So I'm going to use this formula, even though it's a bit longer to write, just so you can see where I'm getting the numbers from. So y2 minus y1 over x2 minus x1. My y2 is my y value of my second coordinate, so that is -1. And then I will be subtracting my y1, which is my y value in my first coordinate, so that's a 2. And then I'll do the same thing with my x's, so my x2 is actually a 3, and my x1 is a 0. -1 minus 2 is -3. 3 minus 0 is 3. And then I write that in lowest terms. I can divide that out. So -3 divided by 3 is -1. So my slope, or my rate of change for this graph, is -1. Okay, that's it. If you have any questions, make sure to send me an email.